Log on, tune in, find out. Another good idea from Cambridge.
First of all, I would like to thank the organizers for the invitation. It's really a pleasure being here. What I'm going to talk about is joint work with Elham Izadi. I'm going to give a generalization of the tetragonal construction and would like to stress on 2 points. First of all, I would like to explain why the existing proofs of the tetragonal construction do not generalize, or at least why we think that we couldn't generalize because them, and then give our proof of the generalization. So let me start with an introduction. Everybody knows the Torelli theorem. It says that the canonical map from the moduli space of curves of genus G to the moduli space of principally polarized abelian varieties associating to a curve C its Jacobian is injective. The tetragonal construction concerns an analog of this theorem to the moduli space of prim varieties. However, we will see that this theorem is not correct in this sense, so the problem is more complicated. So to be more precise, let f of x tilde in x be an étale 2-to-1 covering. To such a covering, one can associate or everything is, I should say, is over the complex numbers. To such a covering, one can associate a principally polarized abelian variety defined, well, I denote it by p x tilde over p, which is defined as the kernel of the norm map of the Jacobian of x tilde to the Jacobian of x. And then this has 2 components, and one has to take the connected component of 0. And then one can show that if you restrict the canonical theta divisor to the prim variety, then this is exactly twice a principal polarization. So where psi is a principal polarization on P. So in other words, we get a map from the moduli space, which is in general called the prim map, from the moduli space RG. R stands for revêtement from the French coverings, and to the moduli space of principally polarized abelian varieties of dimension G-1 associating to an étale double cover the prim variety. So, well, I call it like that. This is the prim map. The question is, of course, whether this map is injective. Well, there's the following theorem. It is generically injective. So PR is generically injective. Which means, i.e., that the degree of the map onto its image is 1. Degree of this prim map onto its image is 1. This theorem has many proofs. Actually, maybe I should write it down. Karnev in 82 proved this for G greater or equal to 9. Then Friedman-Smith at the same time proved this also in 82. And both proofs were non-constructive. Then later, Welters in 85. Actually, I should write this here was for G greater or equal to 7. And actually, I should make the hypothesis here that G is greater or equal to 7. Otherwise, by obvious reasons, it's not injective. So G greater or equal to 7. I forgot this here. Welters in 85 proved this for G greater or equal to 16. And then finally, De Bar in 89 prove this for G greater or equal to 8. And those two proofs are constructive, meaning if you start with an abelian variety here, and you know that it comes from a generic abelian variety in the image, generically in the image, then you can reconstruct the double covering. Sorry?
Is any of this proof by infinitesimal consideration, so that you can recover the curve and recover the differential?
I don't know exactly at the moment. I mean, some are with the singularities of the theta divisor, etc. Right? I don't. Yeah. Maybe any one or I don't remember actually. I mean, this I forgot. At least they are, all of them are different, completely different. Okay, and on the other hand, one has that the map is not injective. So Donagi's tetragonal construction implies that if you have a étal double cover of a tetragonal curve, meaning a curve such that there exists a 4-to-1 map onto P1, then the prim map is not injective at those points. Then, in other words, then you have that the order of the fiber is greater or equal to 3, right? And he conjectured, so which is called by Donagi's conjecture, in this paper, which was actually written in 81, that prim, so if G is greater or equal to 7, then the prim map is injective on the open set of double coverings in Rg, where X does not have a G14. X has no G14. So in other words, if X is hyperelliptic, one knew before, actually I don't.
There are three
Sorry?
for generic.
No, on the open set. It should be injective. This was his conjecture. Actually, this is a formulation of.
In this tetragonal construction, you say that there are three.
Yeah, three.
You cannot make sure that.
There could be more, but this is not known. I think.
But it's only true generically that they are not isomorphic.
So the question is, could they come together over special tetragonal?
According to Donagi's proof, not. Then they are really, yeah. I think I will explain this even, right? Okay. So in particular, also you have non-injectivity on hyperelliptic curves because they admit also a G41, etc. And some trigonal curves, at some trigonal curves you have also injectivity. But anyway, this was the conjecture. Okay. Then in 2004, Vera found a counterexample, namely plane sextics. He showed that for plane sextics, the pre-image has at least two double coverings, right? But then, well, I thought, and maybe everybody else thought, if you consider those curves and the plane sextics, these are exactly the curves of Clifford index 2, less or equal to 2. So I thought, I mean, just the conjecture should just be right here on the space of double coverings of curve of Clifford index greater or equal to 3, and that should be injective. But this is not the case, as we are going to see. This is what I'm going to show. I mean, in fact, I will give counterexamples of arbitrarily high Clifford index. So the situation is more complicated. So So in the first section I would like to explain the setup, explaining what is, how one gets this. So we have a start with an étale double cover of a curve x and have here a map 4 to 1 onto a curve y. But, well, y is arbitrary. So in particular g of y is g greater or equal to 0. If y is equal to 0, this is just a tetragonal construction, what I'm going to explain. Right, so now we look at the following. We take the fourth symmetric product of x to the 4, then we have a map rho to the 4 to x to the 4, symmetric, fourth symmetric product. Then y is contained in x4, namely you associate to a point just the pre-image as a divisor, right? So z bar equal to x1 bar plus x4 bar if this is the if rho to the minus 1 of y is equal to consists of x1 bar, x4 bar with multiplicities. Okay. Then I take the fiber product here, which I call C tilde. This is the fiber product, and call this map F tilde. So C tilde just consists of all the liftings of points here, right? So C tilde consists of a set of liftings z equal to x1 plus x4 of z bar. That's why I wrote here bars, because the liftings are without bars. Right, and you see that every point x1 has two pre-images and so on. So this is of degree 16. Degree f tilde is equal to 16. 2 to the 4. And then now we have to make an assumption. Assume the sequel that the monodromy group, monodromy representation, representation of f tilde into y factors via the y group W of type D4, right? This, for most coverings, this is the case. In particular, if X is, so if Y is equal to P1, this is always the case. So in the original tetragonal construction, I didn't have to make this assumption, but for general coverings, start with the general Y, you have both types. I mean, sometimes it factors, most of the time it factors, otherwise it's not. In an earlier paper, joint paper with Karnev, we also consider the other case, which we call then of W of Y of the Y group of type B4, right? And the difference is, so, I mean, we should write here, this is always the case. But if one has this, then one can show that C tilde is a disjoint union of two curves. C1 tilde disjoint with C2 tilde. Let me explain how this occurs. So, how one gets these two copies. So, denote by dash the involution. So the map x tilde to x tilde, which associates to x dash, just the involution. And then we have this induces an involution which I call sigma, onto C tilde right? So the elements here were these points, x1 up to x4, and we associate to them x1 prime plus x4 prime, right? So we get an involution here. And yeah, so if x1 plus x4 is contained in one of the components, I can say what are the other elements in the fiber, right? Then also the following elements are contained in the fiber. So x1 plus x2 plus x3 prime plus x4 prime, meaning those which have two changes, an even number of changes, and also those which have four changes, right? Right? So this is then the fiber. And C2 tilde are just those which differ by three changes. So for example, it contains x1 plus x2 plus x3 plus x4 prime, etc. And then here, for example, x1 plus x2 prime plus x3 prime plus x4 prime. Right? And since this monodromy factors, you immediately see that sigma x on this and sigma x on this. This is just because here the number of changes is even and here it's odd. So we get this implies that sigma induces an involution on Ci tilde and C1 tilde and also on C2 tilde for I equal to 1 and 2. Let Ci denote the quotient. So Ci I denote Ci tilde modulo the involution. And then we need a lemma which was in the case where for y equal to p1, proved by Welters in his thesis, and for arbitrary y, this is proved in an earlier paper, joint paper with Elham Izadi and with Volker Strehl. This was in 2007. So this means, the lemma says that if rho is simply ramified, that is, every fiber of a ramification point consists of 3 points at least, but ramified, of course. Then, first of all, we have that C tilde, Ci tilde is smooth and irreducible. And secondly, we have that Ci tilde over Ci is an étale double cover, étale 2 to 1, right? And moreover, the genus is the same. G of Ci is equal to G of X for I equal to 1 and 2. So we have the following situation. We have here C1 tilde. Well, we start with X tilde, étale double cover over X, and then this 4 to 1 cover over Y. And here we have C1 over Y, and here we have C2 tilde, C2 over Y. So where these maps are 4 to 1, the genus here is always G, is the same, and these maps are étale 2 to 1. So the genus here is 2G minus 1. Okay, so in all the three cases you have classical prim varieties. I mean, principally polarized prim varieties, right? And I mean, the claim is that the prim varieties are isomorphic. So that's what we're going to see, that the prim varieties are isomorphic, okay? So in the sequel, of course, I only work with one of these components. So I omit the one here. and write now C tilde equal to C1 tilde or C2 tilde. It doesn't matter. I mean, it's the same, right? And also write C equal to C1. Work with this to simplify, right? Now I would like to explain why the proofs why we could not generalize the proofs of the tetragonal construction. Tetragonal construction is just where y is equal to p1. So second section, the tetragonal case. So now y is equal to p1 in this section. There exists, at least I know of, two proofs. The first by Donaghy, first proof by Donaghy. I mean, in his original paper, he didn't give any proof. This was in 81. But then he, in the second paper, in actually 92, he wrote in the beginning that people asked him to write a proof. And he did, via degeneration. The paper is called The Fibers of the Prim Map. Right, so he did this via degeneration. I will not go into the details, but I mean, from this one sees that it's not so easy. At least we couldn't try. Of course, we tried to generalize this via degeneration, but then here he started with simple fourfold coverings and degenerated to more worse ramification, and then analyzed what happens with the corresponding covers here.
You are trying to prove that over the tetragonal locus, the fiber of the prim map.
Well, he looked at. Sorry?
So here the proof of what of the fact that
that they are isomorphic and also that they are different. I give the argument why what he says why they are different. Okay. What did I want? Yeah. Now, if you have genus greater or equal to 1, you can, of course, you try the first thing you try that you degenerate this to a stable curve of geometric genus 0, just with ordinary singularities. But if you do this, already the singularities here get too bad. Actually, you get bad singularities, not anymore as in his case he has semi-abelian varieties and can do something like the same. Here we get very bad singularities, and then we couldn't, at least did not handle this. So, and the other proof is a combination of a result of Welters and of Beauville. So the second proof uses, first of all, Welters criterion. I will write down Welters criterion. This is just a translation into curves by Poincaré duality.
There is a natural map from the frame of C1 pi over C1 to the frame of x pi over x.
In general, what do you mean with singularities or? No, that I will explain. I will give the proof actually.
This natural map, is it just an isogeny? Or
it's an isogeny, and I mean I will explain the whole proof, not even a sketch. Right. Okay, Welters criterion. Yeah, well, I have to be. It says the following. Principal polarized abelian variety of dimension g minus 1. C tilde over C etal 2 to 1. The following conditions are equivalent. equivalent. First, P psi is isomorphic to the prim variety of C tilde over C, if and only if, first of all, there exists a morphism phi of C tilde into P such that two conditions, first of all, the pullback map of P into J C tilde, I mean both are principally polarized, you can identify with its dual, you can consider them as line bundles and pullback, have a pullback. If this pullback map is injective, and second, a phi lower star of the class of C tilde is equal to 2 times G minus 1 factorial times G minus 2 times the class of psi in cohomology. Okay? The proof is just use Poincare duality. This is simple. So now consider the following diagram. We have this x tilde 4 here, this map F4. Well, I didn't give it a name, maybe. Actually, it was rho to the 4. Then we have a map into Jx tilde alpha C tilde, and if you take with the base point C tilde, if you take a base points compatible, this is also compatible, right? And here you have C tilde embedded in here, and here we are over P1. Okay, and the whole map I can denote by phi. Right? Now the point is, if you are on P1, any two divisors of the same degree are linearly equivalent. Any two line bundles are over to P1 are isomorphic, right? So this implies actually that the image of phi is contained in Px tilde over x, which is contained in the Jacobian of x tilde. Right? But this you have only over P1. In general, this is not true for g of y greater or equal to 1. Right? Let me just explain why the how the proof goes on here. Now, before I give the proof of the general theorem. So here we have this map here, phi into P of x tilde over x. And the universal property of prim varieties gives you that this factorizes over P of C tilde over C. You get a map here, right? And yeah, let me go on where. So this was phi, yeah, okay. It suffices to show, according to this Walters criterion, to compute the cohomology of the image of the curve. Right? So it suffices to show phi lower star of C tilde is equal to 2 times G minus 1 factorial wedge G minus 2 of the class of psi in cohomology. Right? But this is actually in this case not so easy. It's easier now. This is contained in J C tilde, right? Here you have a projection onto the prim variety. And one knows that this is multiplication by 2, right? And now one can compute the image of the curve in here. So it suffices to show that I call this map phi tilde. The class of phi tilde star of C tilde is equal to 8 times G minus 1 factorial. This is an 8, wedge G minus 2 psi. And this was done by Beauville. Beauville showed This is a computation of Bouville due to Bouville. Apply McDonald's computation of the Macdonald's theorem for the class. Bouville completes the class of G14 in the symmetric product x to the 4. Okay, and then this comes out. I mean, I omit the details here. And you see, that's why we could not generalize this proof here, because you do not have this here, right? So it's not in here. The image is not in here, and it didn't work. So we give a completely different proof.
Sorry. So it seems that there's two separate statements here. One is that the prim varieties are isomorphic, and the other is that the curves themselves are not, or at least the covers are not.
Yes, I come to that point.
Okay.
Sorry.
So far, we're
I
just
come to
talking
that
about
point.
the isomorphic.
I did not say anything. I'll give the proof now of our theorem and then come to that point. Okay. So let me explain now the result. So we'll see. Here. So the result, third section. So actually, how does one give endomorphisms or homomorphisms of abelian variety? By correspondences. And what we do, we give an explicit correspondence. And this is actually not so. So we give an explicit correspondence, which we call S, Z equal to x1 plus x4, comma, x in C tilde cross x tilde, such that x is xi for some I. That's the incidence correspondence for some I. And we call S transposed the transposed correspondence. So is x z equal to x1 plus x4 in x tilde cross C tilde with the same. Right? Any correspondence induces homomorphism. So this induces, which I call, denote by the small s, of jc tilde onto jx tilde. Not onto, but I mean into x tilde. And S transposed, different, x tilde into jc tilde. Just by adding the points in the Jacobian and subtracting a suitable multiple of a fixed point. Okay? Then the theorem I would like to prove is that S of jc tilde into jx tilde induces, it is not an isomorphism, induces an isomorphism of principally polarized abelian varieties, namely P of C tilde over C with the principal polarization goes to P of x tilde over x with the principal polarization here. Okay, so two remarks. First of all, why is the Clifford index, why do we get examples? Maybe I should start with the other one. Passed already. Why are the coverings different from each other? Okay, so remark one. So remark one, we have to show in general C tilde over C is different from x tilde over x. Donaghy shows this just by noting that, since the monodromy representation varies, factorizes over the Y group D4 of D4, type D4, the automorphism, a group of outer automorphisms of group D of Y group of D4 consists of 3 elements, and this gives just to the 3 different coverings, and 2 coverings here are isomorphic if and only if they differ by an inner automorphism. So in the case where this is P1, they are always different according to this argument. Right? The same argument should be work also here in the general case, but we do this by degeneration, where we degenerate and show that.
Not isomorphic.
not sorry, yeah, not isomorphic. We do this by generation, so we write here in general. Okay, this is the first remark. And the second remark, why can the Clifford index be arbitrarily high? So this is, rho of x, y. If this is simple covering, simply 4 to 1 of a general curve of genus G with ramification degree delta greater or equal to 24 times the gonality of y. Then one easily sees that the gonality of x is greater or equal to 2g plus 2. And since the Clifford index is gonality minus 2 or gonality minus 3, we get arbitrarily high Clifford index here. And this is just a simple consequence of Castelnuovo inequality. Castelnuovo inequality just says that suppose, we have this 4 to 1 map, and suppose we have another, say n to 1, x to y1, say, right, of degree n1. We want it to apply to a gonality here, and right, so that's how one gets this, right? But then one has, according to Castelnuovo, this is less or equal to 4 minus 1 times n1 minus 1 plus 4 times genus of y plus n1 times genus of y1. y1 in our case is 0. So this gives you this, because we have this here, this gives you a contradiction. You cannot have, if you have arbitrary high here, then you cannot have a gonality is smaller. Okay? And this, actually this formula is just the adjunction formula on the surface. Okay? So now let me, so as a consequence of this, we get lots of examples of high Clifford index. Okay, so let me give the proof now. Yes. Section 4, proof. Recall that the correspondences S and S tilde. S was from C to divisors 4 of X tilde by associating to a point Z equal X plus X4, just the divisor. X1 plus X4. Right, and similarly S transpose goes from X tilde to divisors of degree 4 C tilde, just by associating to X the 4 Z which contain X. There are 4 of them. I mean, this is easy to check. Maybe I don't have the time for this. So we have the following situation here, C tilde over C, Y, we call this F, and similarly X tilde, X, Y, we call this G. And then when we note, we need also the trace correspondences. TF and TG are the trace correspondences. Meaning that TF of Z is f to the minus 1 f of z. Okay, etc. Then we have the first lemma. One has to find an equation for the correspondences. Okay, so for all z in C tilde, we have S transpose S of z is equal to 2 times z minus 2 times sigma of z plus 2 times the trace of z. Okay, and similarly, I mean, everything is sort of symmetric. For all x in X tilde, we have S transpose of x equal to 2 times x minus 2x prime plus 2tg of X. Okay? How does one prove this? This is in fact very easy. One has only to show that this equation is valid over one point, because the monodromy factors over the while loop, right? And so if it is valid on one point, this you can extend this. This is a classical trick already used by Turing and Kanev. So we have only to show this at one point. And at one point, this is just a matrix computation. And I will give you how it works. So fix one point x1. Then g to the minus 1 g of x1. Well, we have to take a basis. In order to express this by a matrix, we have to take two bases. So we take the basis x1, x2, x3, x4, x1 prime, x2 prime, x3 prime, x4 prime. And then similarly, suppose z is x1 plus x2 plus x3 plus x4. We have also take a basis there. So f to the minus 1 f of z is equal to x1 plus x2 plus x3 plus x4. This is of course only one point here now. And now you have to take the 7 other points, and we do this in the same way. So it is x1 plus x2 plus x3 prime plus x4 prime, x1 plus x2 prime plus x3 plus x4 prime, x1 plus x2 prime plus x3 prime plus x4, etc. I will not give all of it. Right? So also 8 elements. Then one can work out easily the matrix S, and it turns out that this symmetric matrix, according to these bases, namely, is of this form 1, 1, 1, 1, 0, 0, 0, 0. So it's an 8 by 8 matrix. Here we have 1, 1, 0, 0, 0, 0, 1, 1. Here we have 1, 0, 1, 0, 0, 0, sorry, 0, 1, 0, 0, like this, and so on. The 4 ones here correspond to the fact that in the first 4 elements here, x1 occurs. Okay? Here, in the first 2 elements, x2 occurs, but then not anymore, then only at the end. Okay? And the third one, in the second, x3 occurs in the first one, and also in the third one. So that's why you have this here. I mean, it's easy to work out this matrix here, and then this is just a matrix computation. Just show that the square of this, which is S transpose, is equal to 2 times the identity matrix minus 2 times 1, so this matrix, plus 2 times the matrix which consists only of ones. Right? And now this corresponds to the identity. This corresponds to sigma. Sigma is the involution. Okay? And this is the trace correspondence. Tail corresponds to which I call T0 here, consisting only of ones. Okay? This is the first lemma. Now the second lemma is similar. Lemma 2 first step is S of F upper star of Jy. So recall S is the endomorphism of the Jacobian, is contained in F upper star of Jy. Okay? And S goes from the prim variety here to the prim variety here. And similarly, I mean, the other one, S transposed of G upper star of Jy is contained in G upper star Jy. and S transpose gives an homomorphism in the opposite direction. Okay, and the proof is again very easy. In order to prove this, this is again goes down to a matrix computation, namely to the matrix computation S T0 equal to 4 times T0. And this is the same as this. This is 4 times T0. Right? So this is, one sees immediately, because this matrix has, in every line has 4 ones and otherwise zeros, and in every column has 4 ones and otherwise zeros.
In one, is this an S? The first letter, the S?
S
Yes.
is the, what do you mean?
What is the formula in one?
S, F upper star is contained in the pre-image of this.
And this is the same S. Okay.
This is
An S.
This is small s. Small s was, capital S was the endomorphism here. Oh, I did not maybe write it. Small s, I write it before maybe. Small s, the endomorphism of Jacobians. Right? Right, so it goes from, so small, I will repeat later again, goes from J C tilde to J X tilde. Okay? So this is this, and then we can conclude a proposition from this. Now one knows, I mean, the trace correspondence goes to 0 on the prim variety, because the prim variety is contained in the kernel of a norm map. Okay, so we get, as a consequence of that, we get proposition 1, which says that S and S transpose restrict to isogenies small s of P of C tilde over C into P of X tilde over X. I mean, here we have already the maps, but I mean, they are isogenies. This is here. And S transpose of P of X tilde in X goes into P of C tilde in over C. And such that satisfying the product is 4 times the identity. S transpose S is equal to 4 times P C tilde over C, and S transposed is equal to 4 times the prim on the multiplication by 4 on the other prim variety. Okay, and how does this come? This is of course easy now, because you know proof. Just take the equation of correspondence and take the corresponding homomorphisms of abelian varieties. So this goes into S transposed, small s transposed. This goes into the identity. So, well, we can take out the 2 here. This goes into the identity times 1, and restricted to P, this is given by sigma. So everything also here restricted to P, right? And the point is now that the endomorphism corresponding to the trace correspondent is 0 restricted, when restricted to the prim variety, because the prim variety is contained in the kernel of the norm map. So this goes to 0. So we have this here, and moreover, on the prim variety, sigma is equal to -1. Right? So we get just this is equal to 4. Multiplication by 4, because sigma on the prim variety is -1. Okay, since sigma restricted to P is -1. Okay, so from this we get a corollary. Namely, the degree of S of P of C tilde over C into P of X tilde over X is equal to the degree of the transpose map P of X tilde into X into P of C tilde over C, and is equal to actually 2 times twice the dimension of P, which is actually the degree of multiplication by 2 on P. This comes just from the fact that proof S transpose is a transpose of S. So the corresponding isogenies have the same degree, right? So since the product has degree 4, everyone has degree 2, okay? So now we need a last proposition. So namely that P of C tilde over C, the isogeny here, which is not an isomorphism because it's of the wrong degree, but it factorizes over by multiplication by 2, right? Over P of C tilde over C. So there exists a isogeny psi such that this diagram factorizes. So factorizes via 2 times P. And well, suppose I will give the proof. The proof is also again very classical, and I will give the proof later. But now the proof of the theorem is very, very clear. So since the degree of this is equal to the degree of this has to be an isomorphism. That's everything. Okay, the domains to prove proposition 2. Okay. And this again is a classical proof. I mean, doesn't use anything more or less apart from definition. So recall, so proof of theorem of proposition 2. Recall first that S of J, I mean just to JC tilde goes into JX tilde, and S transpose goes from JX tilde to JC tilde. And what is JC tilde? JX tilde is actually H0 of omega X tilde star modulo H1 of C tilde Z. H1. And the similar JC tilde is actually H0 of omega C tilde dual modulo H1 of, oh no, we have X. C tilde Z. Okay, and then I mean, small s and small s transpose were homomorphisms here. I denote by the same letter now the liftings to the vector spaces, right? By the same letter, not to introduce another letter here. Okay, then let's we use the following standard fact. Namely, if you take the intersection product on C tilde, then this is the same as S of alpha beta on X tilde. This is intersection product, where for all beta alpha in H1 of C tilde Z and beta in H1 of X tilde Z. Moreover, how are the canonical polarizations are given by the canonical polarizations, so on J of X tilde of beta, let me see, comma beta prime is given by minus the intersection product on X tilde. And similarly, on J C tilde is given by minus alpha alpha prime on C tilde. Right? So where for all beta beta prime in H1 of X tilde Z, and here for all alpha alpha prime in H1 of C tilde Z. Putting these two together, we get. Actually, now I have to go to the prime varieties. So let P be P of x tilde over x, and this is W minus modulo pi minus. And similarly P prime, P of C tilde over C, which is V modulo lambda minus, where V minus is a subvector space of H1 of omega C prime, C tilde prime, and W minus is a subvector space of H1, H0. I think H0 of omega X tilde double. I mean, it's exactly the minus one, the anti-invariant part under the involution. And lambda are just the intersection of the lattice with the subvector space, lambda minus and P minus. Okay? So then we get from over, and then the canonical, we know that the canonical polarizations of Jx tilde and Jc tilde restrict to twice a polarization, twice times polarization C prime on P prime and twice C psi on P. Okay? Then from this here we get the following equality. Let me see, where do I do this? Maybe there. Yeah. I get the following equality, E corresponding to Xi prime. This is just the half of it, right, of the canonical. So beta S of alpha is equal to E psi S transpose of beta alpha. Call this star here. This. Right? So for all alpha in lambda minus and for all, I should write this, for all alpha in lambda minus and all beta in pi minus. Okay? Then we have for all now alpha 1, alpha 2 in lambda minus, we have the following. So we want to pull back this polarization. So by definition, the pullback is just E psi S of alpha 1, S of alpha 2. Okay? And now we use a star. By this equality here, we get that this is E psi prime of S transpose S of alpha 1, alpha 2. Now by proposition 1, this was multiplication by 4. Okay, so by proposition 1, we get that this is E psi prime 4 times alpha 1, alpha 2. So from the 4 I can put switch 2 of them over here. So this is the same because this is an alternating form here. I psi prime 2 alpha 1, 2 alpha 2. And by definition this is 2 upper star E psi prime alpha 1, alpha 2. And this means that the pullback polarization factorizes via 2. This is what we wanted to show, right? And this proves the theorem actually. So yeah, this is just, you know, I think the proof is easier. That's why easier than the existing proofs, and that's why I wanted to give it here. Thank you.
Any questions?
The restriction you made originally at the beginning on the monodromy.
Sorry, please.
So you, at the monodromy, you assume that the condition on the monodromy
Yes, yes.
was degree 8
Yeah.
from xi to y.
Yeah.
So what are the other possible?
The other possible, then the curve is irreducible. C tilde is irreducible. Yeah, this is work, I mean,
what is the meaning of this condition?
this is very well explained in Donagi's paper. And also that this is automatic in this condition is automatic in for P1 because P1 is simply connected. This can only come if you have ramification. If you have, let's see, I don't remember actually.
Concretely, so if you start from any x over 1, there exists an eta for which you have such a Moduli condition. This is a condition on the order 2 class which gives us the one-time cover?
I don't know exactly what you mean. But, I don't understand what you mean actually. So this condition is stable under deformation, for example? Yes, yes. Yeah, I think so, yes. I think so, yes. I mean, if it... I'm not sure. I don't know. I don't know.
So,
but it has the two cases. The other case is not... Sorry?
It's not generic.
I don't know, actually. I don't know. But I think this more often you have this case than the other one. That I would like. That I would say, right? In a sense. But I mean, you can easily construct, of course. Thus, these coverings by just taking.
This does not impose the fact that the original map from X to Y has a non-simple, how to say, it can have a simple ramification?
That in any case, in both cases, yes. Yeah. I mean, we in former paper, joint paper with Kanev on degree 3 curves, we have considered both cases and worked this out, the polarization, but for trigonal covers only. I mean, for degree 3 coverings. Both cases, we call this the type B1 and type D1. B1 is, if it's not factorized, in any case, it's a Y group of type B1. But I'm not sure, I don't know what is a generic case. I mean,
if you
I don't know.
Have examples where the ramification of X over Y is simple, then this is your condition is stable under deformation because
but you can deform from simple one to non-simple ones, of course.
I mean, the small deformation.
I see. Yes, okay.
If your condition would impose to have a overlapping point and ramification point, that wouldn't be generic. And do you expect that? Here you have examples where the fiber of the primap contains at least 3 points. Do you expect that there are no?
That I don't know. I mean, this is a good question, but I don't know at all. In the tetragonal case, Debar wrote a paper that there are not more than 3 of this type, but I mean there could be other one which is not orthogonal, right? So it's actually more complicated. One doesn't know actually. I think so. No.
I remember that at that time there was also the trigonal construction, which was the construction which made the prim variety.
These were the first counterexamples by Bouville. I mean, counterexamples to this prim to rally were given already by Mumford in his original paper. For just take hyperelliptic curves, then you can even find positive dimensional fibers just by because every hyperelliptic prim variety of a hyperelliptic is either a product of 2 Jacobians or one of the Jacobians can be 0. But and so this by just dimension count you get positive dimensional fibers. And then Bouville found example for trigonal curves, but just for genus greater or equal to 9, because there are 2 trigonal structures possible.
In that case, the prim variety is a Jacobian?
Is a Jacobian, yes.
And so you do not have a kind of generalization?
No, not at all. No. I mean, the paper I mentioned, who you wrote with Elham and Volker Strehl, we consider actually the étale double coverings of n-gonal curves. right? But then it cannot be, also we're going to have the dimensions of the corresponding primarities are completely different. So you cannot have something like this in any case.
Any more questions? And we thank the speaker again.